So can I do d over dt of this equation? Absolutely. So dq over dt will just be d over dt of EC minus 1 over minus T over RC. Or EC 0 minus E minus T over RC minus 1 over RC. And this will be I on this side. Or I as a function of T will just be EC over RC e to the minus T over RC, where these two will get canceled. And these two will get canceled. And I will be left with I as a function of T will equal yay, current. Okay, so now I'm going to show you a few graphs. And Dr. Faust said that when we come back to the semester, he is going to actually do a lab about this with you guys and show you how these graphs actually work. So for now, I'm only going to show you the graphs. Okay, are we ready? So we can easily find the voltage drop across R and the voltage drop across C by using a voltmeter and an oscilloscope. But for now, just trust me that this is true. Number one, at time t equals 0, delta VR equals E and delta VC equals 0. So the potential drop across resistor is maximum and the potential drop across the capacitor is 0. So in other words, full potential drop across R and capacitor not charged. On the other hand, at time t approaches infinite, delta VR goes to 0 and delta VC approaches the maximum potential EMF provided by the battery. However, at all times, delta VR plus delta VC must equal the EMF. There will never be a situation where the EMF value, the potential drop across R and or V will ever be greater than the EMF provided. Otherwise, our conservation of energy equation that we wrote here will not work. Now, how do I draw this? Assume E is 10 volts, R is 2 kilo ohms, and capacitor is 1 microfarad. What will these graphs look like? Very roughly, the graph for let's say this is delta VC, and this is delta VR, and that's just time. what will these look like? So at time t equals 0, this is at 10 volts. This graph will look something like this, whereas this graph will look something like that. And this will be 10 volts. So now let's write down what we are seeing in these graphs. So this is the charging case. Even though the graphs tell you everything that you need, I'm still going to write them in words. So we said switch closed to position A at t equals 0. So in this picture, at time t equals 0, this connection is made. Okay, what will start to happen? The charge on the capacitor equals 0. At this time, the entire EMF is potential drop across the resistor, which is equal to IR, which means a current equal to V over R is set up such that charges flow to the capacitor, which means the potential difference across the capacitor increases with time. Now we know that delta VR plus delta VC must equal EMF. So that implies that as potential increases across C, what should happen to the potential drop across R? Is that true? That must decrease proportionally? So it never becomes greater than E? That means this decrease in delta VR implies that current decreases. Which means then that the capacitor charges slower. And slower. And slower. Until the current I drops to 0, which implies delta VR also goes to 0, which implies delta VC become equals to E, which means that the capacitor is fully charged. And no more charge will flow.